Alright, how are the levels? Can people hear me? No, stream starting soon, go away. Hello everybody! Welcome to the stream. Yeah, so today's stream is awesome. Thanks, Penmu. So today's stream is the ridiculous idea of taking some delicious, not delicious, taking some incredibly delicious, just exquisite, perfect pesticides and turning them into antimatter, because that turns out to be a thing you can do. Hey, thanks. I'm glad you like the model. If you notice, there's like on my shirt, there's a little thing that's like this weird little symbol. It's like an XT for Xenotime, and actually I can show you. If you remember this little guy from the lore video, there was a little Easter egg. The same XT pattern was hiding here too. Wasn't expecting a model. Yeah, I mean, the only indication I gave of a model was just putting debut in the title. But yeah. So it's time. It's time to turn pesticides into antimatter. Alright, delicious pesticides. I know, it tastes so good. Don't actually eat it. Also, yeah, disclaimer, don't do any of this yourself. Like, it's not that hard, and you can do it safely, but just don't. I don't want to get in trouble. Alright. Is my model tracking? Alright. Alright. So, first I need to get gloves on. Actually, no, let's first talk about Science Edu VTuber universe grows. I know. Why not? What's wrong with Science VTubers? It's just great. VTubers are great. Science is great. Let's do Science VTubers. I love it. Okay, but first, you might have noticed. I'll put one glove on to show you. Teehee. That this says it's boric acid roach powder. So we start with boric acid. That's kind of our starting point for this. And boric acid is used in a bunch of other stuff. It's not hard and you can do it safely. Yeah, but like, just I don't want to get in trouble, okay? It's a disclaimer, not a I'm banning you from doing it. Alright. Okay. So, yeah, we start with boric acid. That's what we're starting with. So what are we going to do? How are we going to turn it into antimatter? Well, it is time for some animations, which hopefully I can get up onto the screen. For legal reasons, do not try this at home. Exactly, yeah. Whoa, I'm in the void now. I've entered the void. Alright, let's see if this works. So, we're starting with boric acid. Let me make this a little bit bigger so that it fills the screen. There we go. All right. Void. I know. Okay, we've escaped the void now. We've escaped the void. We now have boric acid, which is our lovely pesticides. But it is time to put them in the microwave. So what we're going to do is, first of all, we're just going to purify it. That's the first step. So step one is purifying the boric acid to make sure we don't have any contaminants in it. And then the second step after purifying our delicious boric acid is Penrose diagram and ended up in an antiverse. Yeah, slides. I know. I got animations this time. I know some of you were at the earlier stream that I did that was very off the cuff and was organized in my part of it was organized in under 24 hours. I didn't have animations then and stuff, but I have had a little bit more time. I know they look like windmills. They do. Yeah. So this is boric acid. There's a bunch of molecules here, and what we're going to be doing after purifying our boric acid, step one is purify it, is putting it in the microwave and heating it up. Because as we heat it up, it will transform into various different forms of weird boric acids, and eventually, once we reach 530 Celsius it will turn into boric oxide. So why do we care about boric oxide? What's so sick about boric oxide? And the answer is simply that it has a lot of boron in it. So if I go back to the beginning, right, and we look at boric acid, there's a bunch of stuff that isn't boron, whereas after all of this decomposition through heating, we end up with something that is mostly boron, something that has an awful lot of boron. Why is that useful? Well, it's useful because all we care about is these borons. All we care about is these borons. And if we were to look inside these borons, there's two different kind of nuclei we would find. So there's like two different isotopes of boron, which are boron 10 and boron 11. Boron 10 is about 19% of like just naturally occurring boron. About 80% is the more common boron 11. Everyone loves molten boron. Yeah, so we can't get to pure boron because that turns out to be really, really difficult. It's also, because it's so difficult to like make pure boron, it's also expensive to just purchase. And I didn't want to bother with that. We're doing it from pesticides. I do not have, like, there have been people on YouTube, you can find some great videos, who have turned, boric acid into pure boron, and it's quite a process. It's basically, you do a thermite reaction, so you basically just make a gigantic fireball of burning stuff, and it's a whole thing. It's crazy. You can look those up after. But yeah, making pure boron is hard, so we're doing sort of the closest thing that I can reasonably do, which is just getting to boric oxide, because it's still about half and half-ish boron, and oxygen. But anyway, so once we all we care about in our boric oxide is just those borons, and there's these two different nuclei, boron 10 and boron 11, and we only care about boron 10. Boron 10 is the only one that matters here, which is about 20% of all naturally occurring boron. Now, the next thing is, I bet I can, let me turn off my slides for a moment if I can get OBS to not be stupid. Is I have this little guy. No, what is this? This is a radiation source from a smoke detector. It's like actually the smoke sensor, so we can do a little, unboxing here. This is what you would find in a smoke detector. You can rip out a smoke detector and get this. Most smoke detectors, not all anymore, but like there's like two main common kinds of smoke detectors. One of them has radioactive stuff, the other one doesn't. But if you have a smoke detector with the radioactive kind, you'll find something that looks an awful lot like this inside of it. And if the camera will focus or not, that's okay, I can read it anyway. It says, contains a little bit of americium-241. So 29.6 kilobecquerel. That just means that it decays. Like there's a radioactive decay happening about 29.6 thousand times per second. So very, very frequently, this radioactive material inside this little guy here is decaying. And when it does decay, it releases an alpha particle, which is just like the nucleus of helium atom. So we have an alpha particle, which is just 2 protons and 2 neutrons. And it's going to be, about 29,000 alpha particles per second are flying out of this little guy as I hold it. Now, alpha particles can't travel very far at all. They can basically only make it like inside the chamber. As even if you were to have a nice stream of just perfect air. Gosh, I didn't know there were radioactive smoke detectors. Yeah. It's not dangerous, right? It's a teeny tiny, almost imperceptibly tiny amount, but it is cool, and it's very fun for at home radiation experiments, because you can get a radiation source either like this I got 3 of these from cheap for China, but it was a nightmare to ship, and customs kept getting pissed. But the more above board way is if you don't need to access the alpha radiation directly. So in my last video, these things put out alpha radiation, but they also put out other kinds of radiation. Again, it's not dangerous. It's just can be useful for fun amateur experiments. So if you saw the video I did testing radiation shielding, I use those other kinds of radiation because alpha particles can't escape this container. They can't go very far at all. But yeah, we take it's just a mild dose of radiation. You'll be fine. No, it's actually imperceptible. Yeah, you could. I don't recommend strapping this to your testicles or something, but don't do that. But you would probably be fine. It's not dangerous. Why did I say that? Okay. There was a kid in the 80s that made a reactor using old smoke detector. Okay, so that was more complicated than that. Basically, what his idea was he got 400 smoke detectors, stole another 50. And was trying to combine them all to make one big source of radiation. And you can look up David Hahn after this. It was the disaster. He also had other uranium and stuff. This is not, you can't really do nuclear fusion with americium directly. It's really only useful as a source of alpha particles, which is the way the smoke detector works. It basically emits alpha particles on one side, detects alpha particles on the other. And alpha particles are so easy to block that smoke will block them. So as smoke enters the chamber, it blocks some of the alpha particles. And that's what you get. That's how you can detect the smoke. So yeah, anyway, the point is that this thing is an alpha source. It also emits some kind of other radiation that mattered in previous videos. Doesn't matter now. Instantly demonetized. Yeah, we're going to pretend that didn't happen. Yeah, anyway, we have our source of alpha radiation. And so what happens? What happens, you ask, when an alpha particle, which remember, this is putting out, tens of thousands of these per second. Yeah, I remember the story. The kid, it wasn't like that. He didn't blanket his entire neighborhood in radiation. Like, it wasn't that. It was really bad. The contamination was bad, and the EPA had to clean it all up. But it wasn't like a total catastrophe. There have been radiological catastrophes where industrial radiation sources used for blasting cancer cells and stuff like that have just ended up in scrap metal, and through an insane amount of regulatory incompetence ended up just in a pile of scrap metal somewhere. And that has caused genuinely ruined places. You can look up the Goyonja incident if you want. But yeah, that's all that happened. All of that stuff was with really big radiation sources and either an amateur person doing stupid stuff. The contamination was more in his shed. Yeah, right. So it was it wasn't just the radiation flying out of it. Is that now you have radioactive material that's just spilled everywhere, and it was just a whole mess. We will not be doing that, don't worry. I only have 3 of these sources, and that's perfectly... You can't really do anything with those. And I won't be, what he tried to do, with the super dangerous thing he tried to do, and actually, a couple, maybe a month ago, someone on Reddit was trying to do... There was someone on Reddit who had, was trying to basically extract the americium out of this thing and put it in, a test tube. Don't do that. It's that's very, very dangerous and bad. And the last thing I can mention, I guess, on the topic of how dangerous this is that alpha particles can't pass through basically anything. They can't pass through, more than 5 centimeters of air. They can't pass through the walls of this container. They can't pass through your skin. But what they can pass through is your insides. So it's perfectly fine, and it basically isn't the alpha radiation isn't even escaping this container. And even if I had opened it, which we will do a little bit later, it wouldn't penetrate into my skin. It would be totally fine. If you inhale an alpha source, or some, God forbid, ingest an alpha source, then you now have there's not your skin protecting you, and it can be, I think it's about 20 times as dangerous to health as normal radiation. Yeah, it still sounds terrifying. I'd move out of that neighborhood. Yes, it was not good. You should move out of the neighborhood until the EPA cleaned everything up. But it was not some totally nightmarish incident. I mean, okay, it was kind of nightmarish, but for the people just living in the neighborhood, it wasn't nightmarish. We'll put it at that. Anyways, that tangent aside, we have an alpha source. So if I were to open this and expose the actual alpha radiation, what would happen? What would happen to our boron 10 that we have inside our boric oxide? What would happen to our boron 10? There we go. There I am. There's our boron 10. Actually, can I move myself to the other side? I'm moving myself to the other side. Haha. All right, so we have our boron 10 here, which, remember, is inside our boric oxide, so which we get from burning pesticides. Purify pesticides, burn the pesticides, and now we have boric oxide, which contains, a decent amount of boron 10. And what happens when we hit boron 10 with an alpha particle? The answer is this. So I'll play that again, just to see. It absorbs the alpha particle, kicks off a neutron, and turns in to nitrogen-13. So we've transmuted boron into nitrogen, and we've ejected a neutron. This doesn't happen very often. I had to dig through old Los Alamos reports to try to get the number from ages ago. It becomes N12. No, it's N13. The reason it's because what happens is you have, I can do this again. So you gain 2 protons and 2 neutrons from the alpha particle, and then you eject out 1 neutron. So it goes from boron 10 to nitrogen 13. You get 2 protons and 2 neutrons, and then you give up 1 neutron. So in 13, if for those of you who don't know, is just the total number of protons and neutrons. Yeah, so we have nitrogen 13, and very, very rarely this happens. Again, I was digging through Los Alamos reports. It's about between 5 and 10 in every million. So for every million alpha particles that gets lucky enough to hit a boron 10 nucleus, or not even, sorry, the 4 and 10 million is for naturally occurring boron, so it already factors in the fact that not all boron is boron 10. But even still, like, assuming an alpha particle hits a boron atom, it's about a 4, 5, 6, like, in 1 million chance that this interaction will occur. But when it does, we now have nitrogen-13. We've turned our pesticides into nitrogen-13, and nitrogen-13 is radioactive. Now, this is cool. Nitrogen-13 is radioactive, meaning it will. I think that the half-life is like 5 to 10 minutes. So very, very quickly, the nitrogen-13 will begin to decay. And how it decays is rather interesting, because most like radioactive nuclei that you'll just like find in things like smoke detectors or whatever is it basically has too many neutrons, and that's the reason it's radioactive. It's unstable because it has too many neutrons. So basically, you're doing nuclear fusion. Kind of. You're merging technically two nuclei. The official like sciencey name for this, they wouldn't call this nuclear fusion because it's not really like a full nucleus. I mean, it's the nucleus of helium atom. It's kind of borderline. But the official like technical name for this isn't like in parentheses. It's an alpha N reaction because we're putting in an alpha particle and getting out a neutron. And so, all in all, we have damn VTubers and saying thanks. I'm not an expert in this, and I may or may not have just finished setting this up like a little bit before the stream started, but it's fun. I'm happy with this. Okay, so yeah, so it's kind of nuclear fusion, just at like a very, very small scale, and that's not what if you were to like look up stuff about this, they wouldn't call it nuclear fusion. They would call it alpha N reactions. All right though. So we now have our inside our once pesticides, we now have a little teeny bit of nitrogen-13, which is going to radioactively decay. And unlike most nuclei, which have too many neutrons, nitrogen-13 has too few neutrons. And so it's not going to decay normally. It's going to decay a kind of weird way that because it has too few neutrons instead of too many. And what's going to happen is it's going to sort of resolve that debate. It's going to resolve having too few neutrons by turning a neutron into a proton. And oh, what was that ejected out? Oh my gosh, it ejected out an antimatter electron. So that's the way this process works. Is we're starting with boron 10 inside natural boron. Then we hit it with an alpha particle to trigger this alpha N reaction. It becomes nitrogen-13, which is radioactive. And because it has too few neutrons, it will decay by having a neutron turn into a proton, and in the process release an antimatter electron. The normal version of this, where if you have too many neutrons, it'll go the other way around. A neutron will turn into a proton and will release a normal electron. There's also a neutrino kicking out of this, but if you know what that is, you know what that is. We're not worrying about the neutrino. But yeah, that's basically the process. We're making nitrogen-13 sort of in situ here. And then as it decays and turns into carbon-13, it releases a delicious, exquisite, tangy antimatter electron. Positron, the only one with a fun name. Yeah, I've been saying antimatter electron just to make it more clear, but antimatter electrons are also called positrons, and it is a very fun name. I think there's a 3D printer that's like called the positron too. It's just a great name. But anyway, yeah, that's the plan. That's the whole process. We start with boric acid, which will purify. We'll go heat it up until it eventually turns into boric oxide, just to increase how much boron is there. Then some of that boron will have the boron 10 nucleus, and we'll be blasting that with alpha particles. And if we get really, really lucky, like 4 in a million lucky, we'll make nitrogen-13, which will in about 5 to 10 minutes decay, producing antimatter. So yeah, that's the plan. That is the master plan. So I will take this out. And if you have any questions, feel free to drop them in the chat. It's a little bit of a silly chain. All right, I'll put myself back over here. All right. So step one. Step one is putting on gloves so I don't get pesticides all over myself. So we can do that. Does boron 11 not absorb alpha particles, or does it not do anything interesting? So, as far as I know, boron 11 basically, it just slows down the alpha particles. So alpha particle, there's different kinds of radiation that behave differently in terms of stopping them. And alpha particles basically just slow down and just like stop, and then the radiation is effectively gone. And so boron 11, it can interact with them. It'll, if an alpha particle hits a boron 10 atom or a boron 11 atom, it has a chance of either passing through or a chance of just basically slowing down and doing nothing. It doesn't do anything interesting. So boron 11 is just a parasite in our case. There is, you can try to go from like, here's a mixture of isotopes and extract just one isotope. That's what you do with like, isotopic enrichment for like enriching uranium and stuff. But that's extremely difficult, and I don't want to do that. Although it is actually a lot easier than doing it with uranium, because the thing with uranium is it's such a big atom. The different isotopes are like very close in size, right? You have like uranium 235 versus U-238. Those are like, in terms of scale, like those are pretty close numbers. Whereas boron 10 versus boron 11 is like a much bigger difference in scale, if that makes sense. So it's easier than doing it with uranium, but I still am not going to be doing that. All right, now let me see, do I still have the vessel here? We need the little vessel to do it in. So this is the first step. The first step is going to be purifying our pesticides, because if you look at the label, you can see it's 99% boric acid, which is what we want, and 1% other stuff. Again, the other stuff doesn't really matter much from like a making antimatter perspective, but remember that I'm going to be like burning this in a microwave furnace at like 500 degrees, and I'd rather not do that with like random junk that I don't know what it is, just for like safety and stuff. I don't want to, accidentally, make things I'm not planning on making by heating up stuff I don't know what it is. Let me get a little vessel, though. Yeah, what the hell? Let's just use this. Why not? Let's use this. Alright, I got it. So I'm just going to cut up this random plastic thing because it's easier to see with a clear container. Because what we're going to be doing is purifying our boric acid. We're going to do that the most common way that anyone in chemistry purifies anything, which is recrystallization. So it turns out that our lovely boric acid here, well, this is again mostly boric acid, but boric acid, like a lot of chemicals, is a little bit soluble it dissolves a little bit in like room temperature water, but it dissolves more in hot water. So what we're going to be doing is putting in so much boric acid that it doesn't dissolve, heating it up so that all of it will dissolve, because we're now at a higher temperature, more stuff can dissolve. And then what will happen is we'll cool it back down to room temperature. Since there's now more stuff in solution than it can hold, because it's now back at room temperature, that stuff is going to precipitate out as crystals. But the sort of fun trick of this is it's energetically more favorable for boric acid, for impurities to be outside the crystal, right? So when we're forming these crystals, you would either have an awkwardly, like energetically unfavorable impurity like inside the crystal, or the impurity could be totally fine just chilling out there. So this is a very common way of purifying stuff if you didn't know about it already. So let me get some water. And there we go, that's probably good. We just need a little bit. Again, we're not doing this at a huge scale because we just need to make a tiny little tiny chunk of boric oxide. But we can still do this, and now we can try to put in. So we want to put in more than will dissolve, but not too much more. I think it's a little, like we want to do like 30% more. That's about how much extra will dissolve at like boiling water temperatures. But yeah, let me see if I can actually get to this. And the other thing, yeah. It's like the first bit of actual chemistry somewhat. Delicious. Delicious pesticides. And about 10%, yeah, so enriching uranium is much more difficult than enriching like later isotopes. Exactly, it's less of a percentage difference. So let's see, I'm not sure why this isn't dissolving like it did the first time. I guess it's just the nature of doing it live. Nothing works. Let's see if I can get something to stir it with.
Where did my...
There it is. Thankfully, I have some more silverware that I'm willing to donate to science. So that can be our pouring in boric acid spoon. This can be our stirring spoon. I wonder if it's like absorbed moisture from the air since I've had it. Because I basically just opened it and then used it immediately last time. Oh, fuck. Well, first spill, yay. Why is it so hydrophobic though? So the reason it would absorbing moisture would be that it's already in like a hydrated form. I don't remember if boric acid has a hydrated form. But we can see. We can find out. Yummy pesticides. Yum, exactly. Alright. So let's go ahead. I think I put too much stuff in here. Oh, it's going in. Yeah, we just gotta stir a little bit more, and I need to spill less. Again, this is not super dangerous. This is like a consumer pesticide, and most of it is boric acid, which is also used as like a detergent. This is not, crazy dangerous stuff. But it would be nice not to spill it. So I'll just try to stir this around a little bit more. And then let me try to wipe off the sides. Let's see how this goes. And if you have any questions about what's going on or the process or, I don't know, anything, tell me what your favorite type of taco is. Feel free to chat. The knife and the spoon are because you're planning to eat it once you're done cooking, right? Exactly. By the way, very cool experiment. Never saw this. I know. I'd never seen this either. I was the first time I was thinking like, I want to make antimatter. Can I do that? And the most common, like what seems like the easiest way, without just like buying an antimatter source, because that doesn't count. That's cheating. Is to basically make like a small particle accelerator. Because then that'll make super fast or super high. That'll make like photons of light that are high enough energy to split into a matter particle and an antimatter particle. But that's very hard, and I don't really have the ability to do that. But after a bunch of research, I was able to find this method, and there wasn't, there's not really anything about it on YouTube. No one really is like, here's a fun way to make antimatter. It's just buried in the literature as, here's this alpha N reaction that can take place. All right, that should be a bit better. Okay, yeah, so we can see it's like close, but it's not all the way dissolved. So now we will try to get it to be all the way dissolved. I should not have touched that, whatever. With the power of the microwave. This is so dumb. Yeah, so the first step is microwaving just normally. Oh gosh, okay. I need to not spill it this time. Our boric acid will go right in there. I should note, by the way, if you can't see, this is a dedicated science microwave. Don't go doing science experiments in your real microwave. There's even a sign on it that says no food. This is a science microwave. Also, I got it for cheap from some random guy in the suburbs. I'm not doing dumb shit to make it's for me doing dumb shit to make graphs with and post on the interwebs, or both, not food. So don't use a food microwave, even though this is food. What does boron taste like? I'm not sure. I guess I'll find out because I'll be eating the antimatter, not the boron. I'm not sure. Very cool experiment, never saw that. Oh yeah, alright. Alright, so now this is in the microwave, and we're just gonna try to get it to boil the water. That's all we really need to do. So that's the plan. And then once we get to boil the water, it'll hopefully, all of the boric acid will dissolve, and then when we take it out of the hot water, now there's too much in solution, and it will, a very, very pure crystals, hopefully, will start to precipitate out. So yeah, that's the plan. And this is, again, very standard process in chemistry. I can talk about what we're going to do after this, though. After this, we're going to be using this guy, which is my new favorite thing of all time ever. It's a microwave furnace. And so again, I used this in the last video. You can see it's gotten considerably more dirty since then. But basically, the black layer here is a layer of graphite. And graphite is really, really good at absorbing microwaves, or at least like microwaves at the frequency that commercial microwave ovens put out. And so the graphite gets really, really hot. And so because it's so, so hot, it starts to radiate infrared radiation at whatever's inside this insulated box. And so you can use this to heat things up to like almost, pushing 1,000 degrees Celsius, which is like 2,000 degrees Fahrenheit, which is crazy. So yeah, we're going to be using that to heat up. Once we have purified our boric acid, we're going to put a little bit of it on like this little piece of metal that I have just lying around. We'll use a piece of metal. And then we can purify. We'll put our purified boric acid on top of the piece of metal just to hold it. Oh, let's see if it's boiled. And we'll put that in the microwave furnace. Not yet. I'm maybe going to turn the fan up a little bit though. I'm doing this with ventilation because ventilation is good. And you should do things with ventilation. Alright, so I'm not sure if you can see that, but it's not really dissolved all the way yet. And it's also not boiling. And I spilled it. Fuck. Why am I spilling so much this stream? Oh, god damn it. Well, again, I spilled inside the science microwave, where I've already spilled like liquid metal and all kinds of random stuff, so we'll be okay. It'll be okay. Everything will be okay. Alright. Let's put it in for a little bit longer. I will change both anyway. It's not quite molten boron yet. Yeah. You're venting sauce. Wait. Okay. I gotta catch up with chat. That looks like an Oster microwave. Is it an Oster? That sounds familiar. I can't read I don't know where. Oh, it's Insignia. It's an Insignia microwave. I have a cheap one like that. Yeah. So the funny thing about this one, which I mentioned on the sign, is I wanted to get a cheap microwave. So what I did was I don't have a car, so I took the bus and then walked like 20 minutes, it was 30 minutes, might have been even longer, just like through the middle of the suburbs to go pick up this lovely microwave from some random guy in the suburbs, and I carried it back. I'm like walking through like their suburbs where like there's no one outside of a car except me carrying a microwave for like half an hour, and then I just have to carry it on the bus, and everyone's like, what the heck? And I have to change buses too because it's not a direct bus. And I'm just standing, when I'm waiting to change my bus, I'm just standing on the outside of like a tractor supply company in the middle of nowhere, just with a microwave. It was just so funny. What else have we got in chat? Apparently nothing. You still owe me all that graphite for my next drawing. Yeah. It's coming, I promise. Okay, I'll give you your graphite. Mix it. Yeah, I'll see, because the thing is, what we're trying to do is get to, like, boiling water, because that's 100 degrees Celsius, which is, that's like a constant known temperature, right? Boiling water is always at 100 degrees Celsius, no matter what. How much even was the microwave? Like $10 or something? Thanks, random guy in the suburb. Let me change the left stop. Wait, I'm back. Yeah. You're venting sus. I'm venting ventilation. I don't want to get pesticides all over the room. Alright, let's see if this is looking any better. Oh, it is looking better. It might have splattered a little bit, which isn't great, but I'm trying not to burn myself. You can see that it looks mostly dissolved, except some of it is already starting to precipitate out. Let's see. I think that's pretty good. Again, this is mostly just a precautionary step. It doesn't have to be 100% perfect. But yeah, hopefully more crystals are starting to form. Alright, and now we need to filter off, once this cools down a little bit more, will need to go filter off this extra stuff. That's how horror stories begin, walking alone with a microwave. I know, like, I feel like everyone else was probably just staring at me like there's got to be some crazy story. When it was like, no, I just wanted a cheap microwave. I was walking home alone with a microwave when it began. At first I thought it was just my nerves. I began to feel the rumble ominously in my hands. Oh my gosh, yeah. This is material. If anyone is, working on like a writing project, we're offering it. I mean, actually, Rain didn't offer it, but I'm offering it as not the person who made the idea. All right, so hopefully this is starting to crystallize out a little bit. Hopefully you can see that on camera at least. But anyway, we're going to need to filter this. And for that, I know I keep ducking out of frame. That's like what actually is venting. For that, I have what I call the Filteratron 4000, which is a 3D printed funnel and some filter paper that's way too small for the funnel because I mixed up radius and diameter. But that's alright, And there goes my filter paper. Well. Let's, I can probably turn the fan down now that I'm not spilling stuff and shit. Okay. I'm offering it. Take the ball and run with it. Thank you. In college, someone walking around with a microwave is the least weird thing. That's fair. There's definitely weirder things that people get up to. Like making antimatter, $1 funnel for the win. I know, I posted about this on Fetty earlier because it was like, why would you buy a funnel when you can just 3D print one? It's so cool. You can just spawn funnels into existence. Yeah, it's the other thing. I will, the disclaimer about 3D printing stuff is a lot of times you're doing chemistry stuff, you're working with really nasty chemicals that will like eat up all the plastics, and then, all of your 3D prints will just like dissolve. So you have to be careful to check that they're like the plastics you're using are actually compatible with the chemicals you're using. And in this case, it very much is. This is, the funnel's printed out of PETG, which is definitely compatible with even pure boric acid. Which again, this is not even that, it's dissolved in water. So let me try put this in a more stable position. Okay. We got some crystallization out there, and then I will try. Why is nothing flat? Am I just gonna have to turn off the fan? That would be really stupid. That would be really dumb, but I might have to do it anyway. Let's see. Does that stop things from tipping over? Yes, ventilation is good, but unneeded ventilation when everything is tipping over is not good. They will give you physics credit first. I should ask. Actually, maybe I'll show it after. This is my second time doing this. The first time I did it was incredibly janky, and I can show you in a sec. Actually, I'll move this over. I can show you my first version of the Funnelatron 9000, which was not even a funnel. It was just made of cardboard and like the lid of a Pringles can, and the filter was on top of it. We don't talk about that yet, so I'm trying to do things a little bit better this time. But anyway, the first time I did it, I actually wanted to make sure this method actually made antimatter. So in physics lab, we were doing like a gamma spectroscopy lab where it was like measuring the spectrum of radiation. And what happens is when antimatter electrons hit real electrons, which they will do almost immediately, then if the antimatter electrons will hit real electrons, they'll annihilate into just pure light, and it will, because of physics, it'll turn into 2 exact photons of exactly 511 kiloelectron volts of energy. So you have a little peak. And I was able to use the lab's equipment when the teacher wasn't paying attention to ensure that I was, in fact, producing antimatter from these things. Yeah, I know. Just don't, as long as you don't dox me and say which college it is. It's good. All right, anyway, we got some more crystallization going on here. So let's try to pour this in. That's rather slow. Was my first filter better? Oh no. Oh no. It's going so slowly. Oh fuck. It's just ever so slowly dripping down into there. Maybe my first filter was actually better. It wasn't. It definitely wasn't, but that would be funny. Okay. I wonder if... Again, I don't really know what I'm doing. This is definitely not the perfect filter. Like, I 3D printed it. I literally had the opportunity to create any geometry that I could possibly want for the filter, and I created, like, the worst possible filter geometry. Spectroscopy doesn't fit in a container, silly. Yeah. I mean, it's like again, if you watch, like, there's like a debut, like, announcement video thing, which has a bunch of lore stuff, but it starts with me doing the actual measurement, where they basically, in the lab, they had the gamma spectrometer just set up, like, you know, here's gamma spectrometer up top, and then down underneath was the source, and there wasn't really anything else. So that was nowhere near enough, because this is emitting such tiny levels of antimatter and such tiny amounts of radiation. So what I did was they had, like, other bits of lead shielding just lying around the room. So I made, like, a little fortress out of the lead shielding, put it inside. You know, I put, like, some graph paper on the inside so that the sharp, like, bits of the radiation source wouldn't scratch the lead and make lead dust. But yeah, I was able, over about 30 minutes, to measure a very, very slight peak at 511 kiloelectron volts. Yeah, I don't really know what I'm doing, that's true. It's going down, we're good. We can pour a little bit more in. And again, we don't need a huge amount of this. We're just going to put a tiny little dollop of it onto a container. Onto, like, the little piece of metal, and heat that up a crap ton. What isotope did you measure in the lab? There was two, actually. We were doing, like, the first part of the lab was measuring cesium-137. And then after the lab, there was, like, cobalt-60, which is... The idea was that, like, this first part of the lab, we knew it was cesium-37. We knew it was cesium-137, and we knew, like, where the peaks were. And then the second part was, like, you know, we had to figure out where the peaks were, because it was, like, an unknown isotope, except we all knew it was cobalt-60. It said cobalt-60 in, like, the packet and everything. Yeah, I mean, cobalt-60 has quite a reputation, because it's used for industrial radiation sources, which I mentioned. Sometimes industrial radiation sources get, like, misplaced and stuff, and then, you know, through a huge amount of regulatory incompetence, end up in, like, scrap piles. Cobalt-60 is, like, one of the... It's only happened, like, a couple of times. It's not very many times it's happened, but a lot of those times are with cobalt-60. Actually, a lot of the other times are with cesium-137, too. I mean, it makes sense. These are, like, the most commonly used isotopes as radioactive sources. Okay. This filter is going so slowly. My filter, no. Alright, let's... Maybe that'll help, because I do want to get a little bit more out. I'll get another spoon. How's this? I think I did near identical gamma ray spectroscopy earlier this year. That's awesome. It's really fun. I was actually... So funny cobalt-60. Cobalt-60, yeah. I want one of those sources. Yeah. Just notice how your model has two pairs of... Don't worry about that. Don't worry about that. I'll fix it eventually. Alright, that looks like it's filtered down a little bit. I did a near identical... Yeah. So I think it's like a classic... Like, those are the classic sources that people use for both industrial stuff and for, like, physics classroom labs. So let's put a little bit more of this on there. Now, what we're going to do now is try to basically wash it. And we have to be a little careful with this, because what we want to do is get rid of... Like, this is obviously not perfectly dry. Those are vents, not ears. Ventilation. We support safety and ventilation. I love that. Yeah, so what we don't want to do is we don't want to dissolve the crystals. If we add too much water, it'll dissolve the crystals. But what we do want to do is basically flush out, like, this is obviously not perfectly dry, there's a lot of water here, and that water contains impurities. So what we want to do now is just flush out the gross impure water with more pure water. And we'll let that filter down, and then maybe I'll do it one more time. Yeah, there we go. The filter's not clogged. It's going. Yeah, they're vents. I love that. Okay. Maybe I can do it a couple more times then. Again, I'm, losing a lot of the product, but that's okay. We just need a little bit. Just a little dollop of it. As it filters through. That'll be the last one. Alright, and then I will get something for it to leave out. That I can evaporate it on. Do you play games, or is the VTuber model specifically to mask the fact that your skin is irradiated like a gavel from all the antimatter production? No. I don't actually play video games that often. I do sometimes. This is like my first stream as, a VTuber, yay. Maybe I'll play games at some point. I don't know. The VTuber model is just because, like, I want to not show my face and privacy and that stuff. B, it's nice to have a face or something to watch in a stream, so it's not just, like, camera. And C, it's cool. It's cool. I'm a weeb, okay? I'll take that. Alright, that should be our delicious, purer pesticides. It's perfect. I mean, if normal pesticides are delicious, can you imagine how good pure pesticides taste? Alright. Is that going to be enough? I think that's going to be enough. Okay. Alright, now we need our friend. Actually, I'm going to change those. Can confirm VTubers are cool. Says the VTuber. A minor bias. It can be both things. They weren't mutually exclusive. That is true. And again, like the amount of antimatter I'm making is like imperceptibly tiny, right? That the hardest part of this is honestly or not the hardest part, but like it's incredibly difficult to even measure the amount of antimatter that I'm making. I did the math. The estimated amount from like the theory is in the ballpark of one every like 5 minutes or something. Maybe it was more. Maybe it was, I think it was like one every 5 minutes. I can do the math again. But let me get rid of these gloves first. Alright. It's time for microwave furnacing. Cobalt 60. There's actually someone I follow on, like Mastodon, like the Fediverse, whose username is Cobalt 60. It's awesome. There's both. Cobalt 60 exists. It's someone cool I follow on Fedi. Cobalt 60 is the isotope, and Cobol 60 is the programming language, I guess. Don't get these confused. We were informed that if a fire alarm happened, we were to stand around with the sources till someone came and had us sign them back in. Oh my gosh. I mean, the thing with just having sources lying around is only a problem if they're big industrial sources emitting huge amounts of radiation. If you have smaller sources, that's not just like the source lying there isn't a problem. The problem is if it were to somehow enter into your body, right? So if you were to, the idea I assume from that is like if there were a fire and stuff were to catch on fire, that's now no longer contained in a nice little. I have it right here. It's now no longer contained in a nice little package. So it's actually inside here. You'll see it in a second. There's like a foil, and it's inside the like gold foil or whatever it is the tiny amount of americium. And so, like if it becomes not contained anymore, then it's a real problem because now it can enter into your body. So I assume that's where they're coming from with that. Either that or it was a huge industrial radiation source, which would be extremely bad, extremely illegal, and you would probably be very sick. Alright, let's do this. Hopefully this has had a little more time to evaporate. What I will do... How will I do this? That's fine. Again, if there's a little bit of water here, I've washed it, so it shouldn't have impurities. It just should be a little bit wet, which, again, we're putting in a furnace. That'll drive off all the water. And that furnace is right here. All right. So I got this little guy. And now we want to use our last utensil I have lying around. Can use the fork. Actually, let's not use the fork. We'll save the fork. Here's what we'll do. We'll save the fork, and we'll use like the back part of the spoon. Actually, all of them work. Yeah, we'll use the fork. We'll use the back part of the fork. All right, so we'll try to. Again, we just need the little bit of this. Perfect. All right. So now this guy can go into the furnace, and we can close the hatch. All right. Let's put this in. Gotta make sure it doesn't fall over. Wow, I spilled a lot more than I thought I did. Let's clean that up first. Oh, it's all caked on. Okay, well that's actually okay. That's fine. I'll clean it up after. How active is the source supposed to be once it's finished? Is intentional, unlicensed... Okay, wait. Cobalt 60 is an army of 60 kobold wizards casting fireballs. I mean, sure. Fire... radiation. Is an intentional, unlicensed production of antimatter legal? I mean, it's such small amounts. Like, it's not a problem. And again, the radiation sources I'm using are perfectly legal. They're under I'm in the U.S., and so we have the Nuclear Regulatory Commission, and they're well under the exempt quantity limits. It's not a crime. It's not a crime. I'm not doing crimes here. If I was doing crimes, I wouldn't do them live on YouTube. Although if I were to do crimes and do them live on YouTube, I would want to obscure my identity by making a VTuber model. You know, just saying. How active is the source supposed to be once it's finished? I mean, all the sources, every source that I've used, from the Americium ones to the ones in our lab, have reasonably long half-lives in like the tens of years. Americium is in the hundreds of years, actually. So it doesn't change that much. Yeah, I think it was mostly a legal thing with the UK government treating all gamma sources at the same level. Oh, so it was stupid regulations being stupid. I guess that makes sense. They were like, oh, it's gamma radiation, it's bad. Therefore, no, just applying all the regulation to the same thing. That is very silly. That is very, very silly. Okay, let's put this thing in though. And then I will try to give the camera... Wow, the camera's really hot. Hopefully it doesn't overheat. That would be very sad. No, I shouldn't have touched it. Okay, whatever. I'll clean it after. So we need to get to, if you remember from the animation, you know, as you heat it up, it'll go through various different intermediate phases, and then we'll eventually get to boric oxide at about 530 degrees. This thing can get to, again, like pushing 1,000 degrees Celsius. So we should be able to get to that pretty quickly. And you'll see, it'll look like kind of a glassy like layer on top. It looks quite different from just like this weird crystals that we had before. Move that out of the way. So yeah, once we have that, that'll be essentially our target for the alpha particles from our radiation source to hit. And when they do hit it, again, first of all, they have to hit a boron atom and not an oxygen atom. That's the reason I'm doing this with boric oxide and not pure boric acid, is so there's, you know, a much higher chance of it hitting boron atoms. But once it does, there's about a 4 in a million chance that we get the desired reaction, which makes nitrogen-13, which makes antimatter. Alright, actually, how am I going to do this? Last time, it was kind of a pain to break open the source, mostly because I was being careful, because I don't want to damage the actual source. I mean, it's on like a separate metal disc, it's probably fine, but I was trying to be careful. We'll see, hopefully it's not as bad. I can't turn the ventilation back on, though. I should do that. Why didn't I do that before? That was very silly. see how it looks. I don't know if you can see in there. Alright, it is not done yet. Oh, hey, it put it in like different chunks. Huh. Okay, let me, yeah, you can actually feel how much hotter it is from all the like radiant heat from the graphite. What I'm gonna do, yeah, so you can see it looks a little bit different, but it's not the way it's supposed to. So I'm going to add more. I didn't do this last time, but it should be fine. I'm going to add some more onto our little sample here. Just for like aligning everything, I kind of want to have, you know, one nice layer. Yeah, so this is probably, I can't of course say which, but this is probably one of the like intermediate phases as we heat it up. Did it fall over? It did not fall over. Perfect. Alright. I will, while this is going, the only TP roll that is fire resistant is... God, no Taco Bell mentioned. I mean, once you have finished making it, how many becquerels will it have? Oh boy. It's, like, nano becquerels, maybe? I think it's like picocuries. So like nano becquerels. Yeah, it's a teeny tiny amount of antimatter that produces. It's crazy. A sciencer in Australia recently received charges for buying one of those elemental cubes containing like 0.00035 grams plutonium. Yeah, like obviously regulations are good, and you should not be able to go to the store and buy a gram of plutonium. But that's the problem. Is like what you said with your like the UK government. The problem is when you ignore, like you don't pay attention to how much radiation the source is actually emitting. Because again, I have a picture of me just like holding the cobalt-60 source in my hand, right? And it's a tiny little cobalt-60 source. I can just hold it in my hand. You know, everything's fine. We don't even have like Geiger counters and shit. It's basically negligible. And then there's also cobalt-60 sources that are used industrially that like are, you know, incredibly terrifying. You know, you have like 10 minutes, like standing a meter away, like you have 10 minutes until like a 100% chance of death or something. Maybe it's a 50% chance of death, but it's crazy radioactive and dangerous. And it's like they're both cobalt-60. What really matters is the amount of radiation, how much cobalt-60 there is in there. Let's see if this is any better. I kind of doubt it will be. Oh, we're getting there. It looks a little bit different. I don't know if you can really see that. I'll tee it out eventually. It looks a little bit different, but not different enough. And while this is going, I will prepare for the next step, which last time was kind of a pain. And that is basically taking apart our, taking apart our alpha source. Because again, like alpha particles cannot escape this chamber. They can barely pass through a couple of sheets of paper. They definitely can't pass through this like metal. So we're gonna have to open it up. We're gonna have to open it up. And that's actually another thing that makes like the yield of this even worse, right? Is not all the alpha particles coming from the source are just going in basically a random direction. So there's some flying out, this direction, which will, hit our actual target. But there's some flying out sideways that will just not go anywhere. Some flying out, backwards, which won't do anything. So it's even worse. Why did I take the... Let's I'll put one glove on. We'll do it this way. You need to stop burning your gloves so fast. So is this any better? Do I know how to put on a glove? No, it's that. I don't. Alright. Oh, did you see that? It still is like orange. Oh, the graphite's orange too. Heck yeah. I mean, orange hot meats are pretty good. So I'll put it in for just like a tiny bit just to ensure we have, complete conversion. But it's good. We got our oxide. Sweet. Let's check this shit out. There we go. You can see the color because it's like so hot. It's glowing hot. Alright, and I'll wait a little bit for it to cool down maybe. Is it actually done yet? Do I put it in for another 30 seconds? That would be crazy. That would be silly. But I'm going to do it anyway. I want to make sure we have 100% oxide. Because like if the inside's converting to oxide but not the outside, that doesn't matter. The alpha particles, again, they can't really penetrate through much of anything. So they're really only going to hit the outer layer. Let's do 30 more seconds and then we should be golden. Alright. I can also get... Alright. I'm calling it. I realize I'm kind of blocking it right now, but I'll let it. It's hot. That is still hot. So this guy, which I'll leave for it to cool down a little bit. This guy that I'm blocking with my head right now. This guy, there we go. I have fingers. This is our boric oxide target that we've made. And it already cracked. I mean, again, it's fine. But yeah, it's a very, very brittle. It's a very, very brittle layer. So what I'm going to do, move this way. Move this way. Oh, fuck. Ow. Ow. Fuck. That wasn't good. Everything is fine. Everything is fine. This stupid cord. What kind of idiot would put the cord like this? Okay. We're good. Yeah, so you might hear some like popping noises from this thing cracking. Or not cracking, but just like as it's... Because it was at a very, very high temperature, and now it is very quickly gone to not being at high temperature. We can take this guy out of the way, just leave it to cool. Same with our little friendly target. Okay. So we've got our target. We'll bring the camera closer to it. Alright, so hopefully you can see that it's kind of like this glassy thing. That's our boric oxide right there. That was honestly the hardest part of this. We're in the home stretch now. It's almost antimatter time. What I'm going to do now is I should be able to take off my nav. And I'm going to take our radiation source. Should I be doing this here? Or should I not be doing this here? I probably shouldn't be doing this here. Safety. How does safety work? Ooh, shiny. Wait, it's not pico... If it's picocurie, it's not... A curie is 37 gigabecquerel. A curie is... If it's picocurie, it's not nanocurie. I might have done the conversion wrong. I'm pretty sure it's picocurie. But that was an earlier thing. I'll do the math at the end. Yeah, it's not a lot. It's definitely not a lot. Let me grab some more. Yeah, we'll do it this way. Is this ideal? No. Is this what I can do? Why not? Let's do it. I present to you the world's absolute dirtiest cutting mat of all time. But it's the one that I have, so it's what we're using. Alright. So we've got our ion chamber here. We've got our... Let me get this camera in this way. Actually, let me zoom in OBS. Video capture. Wow. 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 Perfect. Heck yeah. Because it doesn't really focus if it's too close. But that should be good. Alright. Stellar. So now we need to rip out this ion chamber and put our target, put our shiny little target inside. And I had an X-Acto knife. It's right here. Yeah. And so we basically just have to get all these little tags and stuff out. Let's how do I put the camera? There we go. So again, we want this little disc inside here in the center holds our actual radiation source. We do not want to bend or damage or scratch, or well, we can scratch the outside, but we don't want to damage that under any circumstances. We just want to get inside our little layer here, and you can see these sides are loose. It's the middle ones over here that it's held on by. And so what I think I can do What the fuck was that? Okay, I know what I'm doing. So little and cute. I know. We got our little cute target. Whoops, there it is. Our little cute target. And our little cute ion chamber, which contains our radioactive source. So this was kind of a pain to do last time. But safety is important. I will not just cut the crap out of this, because that is not safety. It's bad safety. I'm not very strong. Okay. Now I think last time I just broke the plastic pieces. Or did I like fold it? What did I do? This is so dumb. The hardest part of antimatter is opening your fucking source. Yeah, if you heard that pop in the back, that's the microwave furnace. This is like thermal expansion. Oh, yeah, there we go. We got it. Alright, again, you can see this middle part is fine. We're just bending the plastic and shit. Yep. Let's see if we can go at this the other side. There we go, perfect. And we ideally want to break off these metal tabs. But you can already see it. So that little at the very center of that is the actual americium source itself. I mean, you can't see the actual americium, but that little foil in the middle contains the radioactive americium, which is very cool. Okay. Now the only thing I really have to do is get this out. Oh, I heard something. Something went. Can I flip up these tabs now, or no? I can't. Yeah, that's not gonna work. We'll just do the wiggle. We'll give it the wiggle. Come on. Again, you should not be doing what I'm doing. You should not be taking apart these things. Don't do this. Yeah. Come on. You piece of shit. Okay, that's probably good enough. There we go. There's the source. And again, we just need to attach our target on top of the source, which we can hopefully do through the power of Le Hot Glue Gun. Because, I mean, look, we've already used a microwave to heat things up so far. Like, there's no way I'm going to use an actual... source. Okay, it's time, though. This is the big moment of... It's like the Dragon Ball, like, fusion meme. You know, we've got our alpha source and our target. If we put them one on top of the other, we are now very, very, very slowly generating nitrogen-13. We can just go ahead and fasten this guy in place. Oh, hey, look, as soon as I've already done it, it comes free. Oh my god. There we go. That's what I was trying to do. We can bend this back into shape now, though. But yeah, this is our nitrogen-13 source. So we're making nitrogen-13, again, very, very slowly. And as that nitrogen-13 decays, hot glue is perfect mix. Exactly. Hot glue goes perfectly with radioactive sources. Yeah, so this is slowly making nitrogen-13, and in about 5 to 10 minutes, this is the half-life of nitrogen-13, and when it decays, it makes that delicious antimatter. How cool is that? How cool is that? Alright, and then I'm going to want to put the lid back on, just because, partly to keep this all safe, but also the lid has like a label saying like radioactive material. So how do we know if it's working? Well, I don't have the ability to test this particular sample that I made, but if I go grab this, it's like seeing double. This is the original one that I made, and what I did with this one is I put it inside a gamma spectrometer to measure gamma rays, inside like some shielding. And when an antimatter electron hits a normal electron, which it will do almost immediately because our world is full of real matter, normal matter, not antimatter. When it hits a real electron, it'll just annihilate and turn into 2 gamma rays of exactly 511 kiloelectron volts of energy. And so when I took this source, this was the original source, which again I did using the exact same process I did here, and I measured the gamma spectrum, and there was a peak at 511 kiloelectron volts. So we know that this guy is making antimatter, and I mean this is just me doing the whole procedure again. But yeah, that's how we know. It was if you go to check out, like, if you saw, it was at the very beginning of like the debut like announcement video. So you can go there. Will this camera not be stupid? Okay, thank you, camera. I appreciate you not being stupid. All right. So let's close the hatch though. Let's finalize this up. Just yeah, we'll just I mean, this doesn't really matter that much. I'll fold these tabs up just so they don't poke into things. Whatever. And then we'll close up our very not janky, very, very legit, hot glued together antimatter source. Which ow. Fuck. There we go. Our antimatter source, which, as the video title, or stream title I guess, suggested, is in fact made from our delicious, delicious pesticides. Which is really cool when you think about it. Like, I mean, come on. Making antimatter from pesticides? It's almost as cool as this camera is stupid. But yeah, here it is. I mean, that's what we've got. That was what this stream was about. We were making this thing, which is making antimatter, and I mean, it was also the debut to show my model that I made. Time for the taste test. I mean, unfortunately, antimatter electrons can't travel very far at all, like outside of vacuum. So, people use them in particle accelerated stuff. They have a perfect vacuum. But not in vacuum, they'll hit a real antimatter. They'll hit a normal electron almost immediately and annihilate into, as I said, 2 gamma rays. This is flaming awesome. Thank you. I'm really glad you like it. I hope this was a fun little debut stream. I think this is really cool. I think antimatter is freaking wild. But yeah, this thing is producing antimatter at a very, very slow rate. What can I say? We turned pesticides into antimatter. So yeah, if you have any more questions, feel free to let me know. I will do my best to answer them. And while that's going, I will. This was very cool. Thank you. I'm glad you liked it. I will try to quickly recalculate the how much this is actually producing per second, because it's a rate of, let me see, it's a rate of 4 in a million is the conversion. Then we'll assume boron and oxygen atoms are the same size, so that should be fair to make. So we'll say it's 2/5 chance of it hitting a boron atom, and then 0.5, because the particles are emitted in every direction unidirectionally. So some of them go out this way and hit our target. Some of them go out this way and just don't do anything. So if we multiply those together, and then we need the actual rate of alpha particles in the first place, which it so handily says on the device itself. Maybe you can see if I get the lighting right. There we go. 29.6 kilobecquerels. And a becquerel is just 1 decay per second. So again, this is decays of the alpha source. So we're producing about that many alpha particles per second. 29,600. So that should be a rate per second. We can divide that by, or multiply that by 60 to get a rate per minute. So it's about 1.42 antimatter particles per minute. So, yeah, not a ton. Not a lot. But it is still happening. And actually, when I made the, let me grab the actual spectrum itself so I can show you guys. When I made the, I was in the physics lab and I took the spectrum to prove that, where did it go? With the old one to prove that it's actually making antimatter and this process works. I can go find that spectrum actually to show you guys. But yeah, so it's about, if I, divide this, do 1 over, it's about 1 antimatter particle every, is that right, 70? Oh wait, 0.7, that's of a minute. It's about 1 antimatter particle every 42 seconds. Hey, 42! It's the answer to life, the universe, and everything! We did it! It's the answer to life, the universe, and everything! It's about 42 antimatter particles per second! Or per minute, sorry. 42, wait. Sorry, 1 antimatter... I'm so dumb. 1 antimatter particle every 42 seconds. Which we know is correct, because 42 is the answer to life, the universe, and everything. Teehee. Yeah, let me grab the actual spectrum to show you, though. Fair enough, better than 0. I mean, yeah, 0 is the normal one, and again, it would be, it's more dangerous if I have less. Where is it? There we go. I gotcha. So let me, download this, and then what I can do is go to my Vroid model here. And there we go. How does that look in VS Code? Not VS Code. Am I back? Where am I? There we go, I'm back. What I meant to do was to show the spectrum So let me add a source. Sorry for the OBS fucky. No, not that. Pipewire application window, image viewer. There we go. There we go. So this is, if I put it so you can actually see me, there we go. So this is the spectrum. This is the spectrum that I get from the spectrometer. So this big, huge peak, which goes off the screen, is gamma rays produced, like radiation produced by the actual alpha source. So we're not detecting alpha radiation, but in addition to producing alpha radiation, these sources also produce gamma radiation at about 60 kiloelectron volts of energy. I actually used that in the previous video, but that doesn't matter. What matters is these two little peaks that you can barely see down here. Again, this was done with shielding for 30 minutes-ish. You can see there's very roughly two peaks. And the second peak, I don't know what it is. It's very close to the peak of cesium-137. So my best guess is that the cesium-137 source that we had in the lab, or maybe cesium-137 contamination was making its way, through the lead shielding anyway, and making a tiny little peak. But this other peak is about 511 kiloelectron volts of energy, and 511 kiloelectron volts of energy. That's what happens when antimatter electrons hit real electrons and they annihilate. So, yeah, that's the proof. Again, it's such a tiny peak, but it's where I expect it to. And the other thing I wanted to say, because we were talking about the number of one positron every 42 seconds, it's actually quite consistent. This reading is quite consistent with that calculation I had done, because we know how many alpha particles are. We can estimate how many alpha particles are emitted based on how much gamma radiation we detect, and in comparison, that so we know that you can see there's the scaling factor. It should be a little under 1 in 1 million, and that's about what we see. The peak from not antimatter, just normal radiation being emitted by the alpha source is about 1 million times bigger than this tiny little peak from the antimatter electrons. But yeah, that's what I got. Better than 0, 42. I know, it's the answer to life, the universe, and everything. Unreal. Very different software than what I used. Yeah, I think it was called USX or something. There's a bunch of different ones to read these gamma spectra. Yeah, we had a kind of stupid setup too, where we had because there's different ways you can analyze gamma ray spectroscopy data. There's you can either look at a single channel, which is the old dumb way, or you can look at the way everyone does it these days with a multi-channel analyzer, it's called, where you have basically you get a spectrum directly, you get a spectrum like this, right? Each of these, each bin corresponds to a channel, and then you can plot it all at once. But for some reason, we had our actual tube was being powered by the old style, so it went into a single channel analyzer, which you can think of as just reading only one x coordinate of these at a time. So we were using that to power and do the amplification, and then we were passing the amplified signal into the multi-channel analyzer. I'm not really sure why we did it that way. That was kind of weird. But yeah, that's what I got. So, I think I've hit on everything I need to hit on for the stream. If anyone is still around also and not in the Discord, there's a Discord. There should be a link to it in the description. There isn't a link to it in the description of this. I can add that now. But yeah, thanks so much to everyone for stopping by and getting to see me make some delicious, yummy antimatter out of pesticides. Because why not? Why the heck not? And I'll put the Discord link. I'll put it in chat too. What is this? Yeah, we used an MCA. Ours created the bars, making it easy to read. Yeah. So it was we had again, it's the same thing. The actual data was coming from the MCA. This is a different style, so it makes it the scatter plots. It shows the scatter plot thing rather than just one number for each of them, or for each of the bins, which again is very helpful when you're looking for such tiny signals. Yeah, here's the Discord. Link in the chat. Owler says it was really cool. Thanks so much. I'm glad you guys liked it. Penbu, thank you so much. Congrats on debut. I know, I'm a VTuber now. I did it. I'm a VTuber. Yeah, so I definitely have lots more. I have lots more fun stuff planned. And yeah, I'm really excited. I'm glad this worked out and nothing went catastrophically wrong, which was maybe on the cards. But yeah, thanks so much to everyone for stopping by, and I hope you liked it. See you. I'm definitely going to be doing more streams, so see you in the future.